Okay, so we're going to start today with second order differential equations. Okay. Okay, so that's going to be our next part of this, and this will be the last type of differential equations we look at, but there's quite a lot of different categories in here, okay? So there is a fair bit of notes coming. We won't finish this just in this video today. So I'll show you what the form looks like and how it's totally different from anything we've seen. So second order linear equations have the form a d squared y by dx squared plus b dy by dx plus a value c attached to a y equals some function of x on the right hand side. Okay, and a, b, and c are just constants. Okay, so they're constant values in front of each term. So you can see that the main difference between anything we've seen before is that it's involving the second derivative into the equation. Okay, and that's the minute you see the second derivative in the equation, it's asking you to solve a differential equation, then that's when you know you're in second order. Okay, all the ones we've seen before have only had dy by dx in the questions, whether it's been separable or linear. Here, it's second order all the time when you see that. Okay, so it's quite it's a very unique way of just spotting it all the time, just if you see that. Okay, so what we have is we've actually got two cases of second order equations in here. Okay, and it namely comes down to the f of x function. Okay, so we have two cases. Don't know why I've got an apostrophe there. I'll rub that out. No, that's not what I want to see. Here's my thing with. There we are. We have two cases of second order equations. Okay. So the first case is when f of x equals 0. So in other words, there's no function on the right hand side. Okay, that's actually the nicest category, I think. Okay, because there's less to deal with. So when f of x equals 0, now there's been a bit of a difference in opinions last year. I'll write the word down and you can see how you would say it. I would call that homogeneous, okay? Now, I know other people call it homogeneous, so whatever you've heard in whatever category or other subjects, okay? But it's called the homogeneous equation, okay? When there's no right-hand side, f of x is 0, okay? In the other case is when f of x doesn't equal 0, so it is a function of something on the right-hand side, some function of x. Then we call that the non-homogeneous equation. Okay. So in this video today, we're only going to focus on homogeneous equations. Okay, I'm not going to do any examples in the video about non-homogeneous equations. That will come after. Okay, so that's just the two different types. So let's start off with homogeneous equations. Thank you, yeah. Should have been a score for the non-equals. Thank you. Homogeneous equations. Okay, so because it's homogeneous, we're only looking at equations today of the form a equals d squared y, sorry, a d squared y by dx squared plus b dy by dx plus c y equals 0. Okay, so we're just going to focus on the right hand side of 0 today, okay? So when we solve this, the first thing we do is we rewrite it to help us work out what category we're going to be in, because there's going to be 3 different categories in this section, okay? So this can be rewritten as, and all we're going to do is we're going to swap the differentials for a capital letter D. Okay, so it's going to be a d squared plus b d and c. Because it was just y, no differential, we'll just keep that as c. Okay, equals 0. Now we know from National 5, if I was to solve something like this, so in other words, you'd have seen it a lot with x's, there's 3 different possibilities of roots you get with these equations, okay? So we know there's 3 possibilities. Okay, of roots. So the first one is that we could have 2 distinct roots. We'll call them D1 and D2. Okay, so we get 2 different roots from each other in some categories. And what that would do is, if that was the case, then the general solution to solving that second order differential equation looks like, general solution will look like, sorry, not equal straight away, let's go back to y equals, and then it would be a constant a, e d1 x, plus a constant b, e, second root to the power beside x there, okay? A and B are different constants to what the lowercase a and b were, okay? They'd be brand new constants that if we had some data for, we'd be able to work out. But the general solution, if we've got 2 distinct roots, so 2 different roots, then the solution to that equation at the top would have been in the form constant with the exponential of the first root attached to it, and then a constant with an exponential to the second root attached to it. Okay, we okay with that so far? Alright, so that's the first root, 2 different roots. Okay, then if we go to case 2, then we could have equal roots. Okay, so in other words, 2 roots but the same, equal roots. So they'd both be the value d1. Okay, and what that would give is a general solution of y equals ax plus b e to the power of d1, which was a root x. Okay, so you can see it's very similar to what the first general solution looks like for type 1, 2 distinct roots, but there is a difference regarding there's an extra x attached to one of the constants, and we just have 1 root, so 1 exponential there. Are we okay with that? Okay, then we get to the third root, which before we would have known as no real roots, but we've just seen in the previous video that we get complex roots now. Okay, complex numbers come up, so complex roots. Okay, so that would be in the form p plus and minus qi. Okay, so p and q would be real numbers, but we would have an imaginary number there if it was complex roots. Okay, and we still have two roots because one would be the plus form, one would be the minus form. Okay, how that would look though as a general solution, well, there's a bit more involved with this one. So the general solution would be y equals e to the px. Okay, so your real part, the bit that's not got an imaginary number attached to it, would go on the exponential. E to the px bracket, new constant a, then it's cos of qx plus b sine of qx. Okay, so depending on which category we're in will depend on how our general solution will work. Okay, but what we get for our roots we use to get our general solution. You okay with the three different types? We'll now look at an example of each type to show you how we can do it. Okay, so before we do that though, just before we jump to our first example, there's one little bit of notation I still need to inform you on, okay, which will be very important for us, is that the equation that we changed our original form to, okay, so the equation that was AD squared plus B times D plus C, okay, equals 0. This is called the auxiliary equation. The auxiliary equation. Okay, and we can denote that, and maybe highlight that as well, the auxiliary equation, which is denoted AE. Okay, so that's what we need to do at the start of every question, is we'll need to work out the form of the auxiliary equation and use that to get our roots. Okay, so we'll go to example 1. So solve d squared y by dx squared plus dy by dx minus 6y equals 0. So that's our question. Okay, we want to find the general solution for that. We don't have any data to find any particular solution, so we need to find the general solution for this. Okay, so going to our auxiliary equation, I'm going to swap all the differentials with the letter d. Okay, so because that's d squared y by dx squared, that's going to be d squared there. Put that in brackets there, auxiliary equation, plus d for dy by dx minus 6 equals 0. Okay, I'm going to solve that there. Now, we could use a quadratic formula, but you can quickly see that this factorises as a trinomial. So that would be d plus 3 and d minus 2. Okay, that would work in there. Therefore, that would yield me the roots d would equal negative 3 and d would equal 2. Okay, so I've got two distinct roots here, they're both different from each other, so I'm in case 1. So the general solution, and I'm going to use the notation g dot s, okay, so the general solution would be y equals constant a with one of my roots, let's go for the first one, negative 3x, plus b exponential to my other root, 2x there. Okay, that would be the general form of the equation that would solve our second order differential equation at the top. Okay, that's what the function would look like there. And if we had data, we could work out a and b. Okay, with example 1? Excellent. Okay, we'll go on to example 2. So again, let's see another equation. So let's solve d squared y by dx squared plus 4 lots of dy by dx plus 4y equals 0. Okay. So what we need to do first is write down what our auxiliary equation looks like. So that's going to be d squared plus 4d plus 4. You get a lot quicker at writing these. equals 0. Okay, that would actually give me the answer as I factorise it d plus 2 squared. Okay, you get d plus 2 in both brackets if you don't have a trinomial. Therefore, that would give me an answer that both my roots were in fact minus 2. D equals negative 2 there. So, general solution is that y equals ax plus b e, and we put our root up, which is negative 2, so it's e to the power negative 2x there. Okay, that's what my general solution for that one would have been. So that was category 2, that we were in the same root, so I had to write a general solution like that. You okay with that one? Okay, and last but not least, let's go to example 3. Let's look at one that will have complex roots. Okay, so let's solve. I better write the word solve in. Solve d squared y by dx squared plus 2 lots of dy by dx plus 5y equals 0. So our auxiliary equation is going to be d squared plus 2d plus 5 equals 0. And this does not factorise. So we'll go to the quadratic formula. So a will be 1, b will be 2, and c will be 5. So if I put that in, our value for d will equal negative 2 plus or minus the square root of b squared minus 4ac. So b squared is going to be 4 minus 4ac is going to be 4 times 1 times 5, which is 20. All divided by 2 lots of a, which will be 2. Okay. So it's going to equal negative 2 plus or minus the square root of negative 16. Okay. And if I split root negative 16 as root 16 times root negative 1 divided by 2, I'll come back to the to finish this off. That's going to give me negative 2 plus or minus. Well, the imaginary number I that we've seen in the previous video is negative 1. Root 16 is 4, so it's going to be 4 lots of I divided by 2. And if I divide both of these by 2, I'm going to get negative 1 plus or minus 2i. So we've got ourselves complex roots. Okay. So once I've got my roots of that form, we'll put into the general solution. So the real part of my complex number, so the bit that doesn't have the imaginary number attached to it is negative 1. That goes on to my exponential. So it's going to be y equals e to the negative 1x, or e to the negative x, we'll write after this. A sine, sorry, it's cos first, wasn't it? It doesn't really matter because you just know it's going to be sine and cos, and they would work either way. But we'll keep the right form. A cos, and it will be 2x plus b sine 2x. Okay, so the number that's attached to the imaginary number goes in beside our cos's and exponent sine functions. If I just rewrite that a bit nicer, that becomes e to the negative x, a cos 2x plus b sine 2x. You okay with that? Okay.